Hello. In this video, I'm going to be talking to you about Math 3, Unit 6, Objective 5, Proving Mathematical Conjectures. Part 2, actually, or Day 2 is what it says. And before I begin talking to you about this unit, I want to show you briefly what happened in Day 1, because you may choose to skip that, and I just want you to know then what decisions you have to make after that. So Day 1, I'm going to show you the teacher's key to the notes, because we're not going to really talk through it that much. This is in Google Drive. You could print this out. So in this day that we will probably skip because it gets a little bit extra complex, more than what we need, they take these same numbers that we had, sets of numbers that we had in 6.3, and they're going to prove things algebraically about them. Some of the same conjectures that they made or they examined as true and false in Day 3, they will prove to be true or false in Day 4. And so the problem then being they need to understand how to algebraically represent an even number, an odd number, a square number, and an oblong number. And especially even and odd are not necessarily intuitive to them. And so we go through this activity in the notes to get them to believe that an even number can be written as 2n, and if you want to get to the next even number, it would be 2 times n plus 1. An odd number can be written as 2n minus 1, and if you want to get to the next one, you would have 2 times n plus 1 minus 1. This could also be 2n plus 1. If you remember back in the days of your number theory courses, anything that gets it to not be an even, either one up or one down, will be an odd. And so it becomes a little bit complicated. The problems that were in that assignment were problems like these. 3 times an even number plus 4 is an even number. And so we take 3 times 2n, which is a sample even number, and add 4, and we then work that out. And because we can factor out the 2, so we have 2 times something, it could be anything, then we know that that's going to be an even number. Well, that's kind of complex. We're probably going to want to skip that this time. So consequently, anything that comes up about evens and odds, we're going to want to skip on future worksheets if we skip it on this one. But it's a nice assignment, and it does let them prove some of the conjectures they had the day before. I still think it will be something to save for a different year. So on Day 2, we have things that don't need even and odds. And so that's the ones we're going to be looking at today. This problem number 1 doesn't have anything to do with even and odds, and we're going to actually work that one together. Problem number 2 does have something to do about evens and odds. Pick any odd number. Because of that, it builds on the information from the day before, from 6.4, which we've skipped. So problem number 2, you will want to skip this year as you do that. Now, that being said, if you have an honors class, it's a fabulous little proof because it practices some of our rational function, like getting common denominators and things, adding with a common denominator, things like that. So it's a nice proof, but it's pretty challenging. It's definitely the hardest of the 3, and it does use an odd integer. So if I was going to do this because I had a more advanced class and I had the time, then I would give them that they needed to write an odd integer as 2n minus 1 and work through that. But for almost every class, I would say skip number 2. That makes it a 2-problem assignment, really. We're going to do problem 1. We're going to do problem 3. Problem 3 is actually straight from the standards, the California State Standards. And so this is one that we would like to do. There's also a bonus, which I would skip. Every Pythagorean predictor that I've found online is pretty challenging to prove and does use even and odds, and so I would skip that for now. I would just run this off as a back-to-back problem number 1 and problem number 3. That's all I would do. So let's look together at those 2 problems. Here is, pardon me, I'm going to turn the page one more time. Here is problem number 1. And I wrote that out. It says Jeremy thinks he has found a shortcut for squaring numbers that are something and a half. For example, to square 6 and a half, you multiply 6 times 7, just by 1 greater, and then you add a 4th. Investigate by trying 3 number examples. So what we need is something and a half. So I will try 3 and a half, And if I do 3.5 and I square it, if I have a calculator, then I can make that 3.5 squared. I'm sorry, 3.5 squared, and I can do it that way and just pull that answer. If I'm going to do this by hand, I would probably say 6 7/2 squared is 49 fourths, which that goes in there 12 1/4. If I square this on the calculator, it comes out 12.25. Okay, so now I'm going to try his shortcut. So I either want to get 12 1/4, 12.25. So his shortcut said take the 3 and multiply it by the next consecutive number, 4, and then add a fourth. And lo and behold, I'm getting 12 1/4. So this did check for 3.5. I need to do 3 times. Investigate by trying 3 number examples. And we know from 6.3 that it being true 3 times still doesn't prove anything, but it is sort of convince us that it might be true. And if we find one that's false, we know that we don't have it. And so the next one I'll try is 1.5. If I have 1.5 squared, I'm going to think of that as 3/2 squared, and that would be 9 fourths, also known as 2 1/4. And if I want to try that here, I would go 1 times the next bigger number, 2, is 2, plus 1/4 is 2 1/4. So that did also check out. And then we'll just try something bigger like 10.5. 10.5 squared I could write as 21 halves, which is, when I square that, is 441 over 4, which is 11 1/4. Did I get that right? I must not have that right. Just 110 1/4. Just kidding. I lost a 0 there, just like the kids do. 110 1/4. Goes in 1, goes in 1, goes in 0 times with 1/4 left over. Good. And then checking the other way, by Jeremy's shortcut, I would say 10 times 11 plus a fourth. So that would be 110 plus a fourth, and that would be 110 1/4. And so it checked. And so Jeremy seems to be onto something. His shortcut seems to be working. If I didn't have a calculator, this would be a good way to square something in a half. Especially, see, when I got up to here, it was harder to do this in my head. This was really easy to do. So I like that. So we're supposed to give a precise statement of the conjecture using variables. So first, what we're wanting to do is we have a certain number and a half. So if I let the original number be n plus 1/2, that's a certain number and a half. And I want to square that. What it's going to be equal to is that number, n, times the next bigger number, n plus 1, and then add a fourth. And so that would be a variable statement of the conjecture. Students might have a lot of difficulty with that, and so guide as much as you need on that. And now their plan is, and I imagine that if I was doing this, we would probably do one of the two mostly together in class, and we would send home the other one or have them work in groups on the second one. They might not have very much homework on this. If it fell on the block, that would be great, because then one of the two assignments you wouldn't have much homework. So after that, you're going to try to prove that that's true. So let's look at that statement. I'm going to rewrite that. It says, using the way that you wrote it, prove the conjecture. So what we had, again, was n plus a half squared equaled n times the next bigger number plus 1/4. And now we're going to see if this works out. So we need to do n plus a half times n plus a half on this side, and I will get n squared. And I'm just going to do one step at a time, because the kids are going to be freaked out about the fractions. So n times 1/2 will be 1/2 n. And then this one, n times 1/2 will be 1/2 n again. And then a half times a half is a fourth. So adding up those like terms, I'll have n squared plus 1/2 and 1/2 is 1n plus a fourth. And now checking this on the other side, right? I'm checking this on the other side. I would distribute in this n, and I would get n squared plus n plus 1/4, and that's it. And again, I would accept from the students working both sides at this point. We have advanced math where we can teach them to work only one side. If you are wanting to have them work only one side, then and you are wanting to work this side entirely to get that side, then you could have them factor an n out of this first part, because they see they're going to keep the plus 1/4, and then they'd have n and n plus 1 plus 1/4. But I would say at this level of student, just having them work the algebra on both sides and see that it's true is appropriate for this level of student. And when we get to advanced math, then having them actually complete a proof entirely on one side to equal the other side would be fine, like a trig identity would be fine. The I lost track of what I was going to say. We're going to go on to the next problem. So let me show you the second problem that we're going to skip on this for a minute. So this one that I said you would maybe skip is a really interesting one. It's very engaging. The kids like to figure this out. Excuse me. And so it says pick any odd integer. This is your first number. So they're going to pick an odd integer. For an example problem right here, I'll pick 5. Square it. Okay, so then I would have 5 squared is 25. Divide that by 2 and you get something and a half. Yep, 25 divided by 2 is 12.5. Okay. And round down to get your second number and up to get your third number. So if I round down, I would have only 12, and if I round up, I would have 13. It says those three numbers are always the sides of a right triangle, 5, 12, 13. Lo and behold, that is true. 5 squared plus 12 squared does in fact equal 13 squared, and that's true. And in fact, no matter what odd number you pick, that will always be true, and it can be proven to be true. One thing is you don't really want to pick any odd integer. If you pick 0, that's not going to work out so well for you. And so negatives don't work very well because you can't have a negative side, so it needs to be a positive odd integer. So when you try to write that, what you get is something a little tricky. You're going to have an odd, so maybe 2n minus 1 squared. The first number is just the odd, 2n minus 1. And then this, you are going to, after you square, you're going to divide it by 2. And then basically to round down, we subtracted a half, and to round up, we added a half. And so your second number is going to be this minus a half, and your third number is going to be this plus a half. And to show that that's a right triangle, what you would need to do is 2n minus 1 squared, your first number squared, plus this second number squared, and that should equal this third number, 2n minus 1 squared over 2 plus a half squared. And so the math on that is pretty complex. The idea of representing the odd number like this is pretty complex. This is one to skip in almost every class. But in honors class, it's a nice proof, and the kids love learning this shortcut. They love learning that shortcut. It's rewarding to be able to prove that it's true. So that being said, we'll skip that one for this time. But it's a nice challenge problem. It'd be one you could give them as a bonus problem on a group quiz or something like that. It's very fun. So the third one, the one that actually comes from the standards, is this one. Trina found a different way to make Pythagorean triples. That's why it says a different way. So if you've skipped problem 2, you might like to delete that different out of the worksheet so that it doesn't say a different way. And hers is pick any 2 integers. Look at the sum of the squares, the difference of their squares, and twice the product of the integers you choose. These are the sides of a right triangle. So investigate. So any two integers. I'm going to use for x, for my first integer, I'm going to use 3, and for y, my second integer, I'm going to use 4. Look at the sum of the squares, the difference of the squares, and twice the product of the integers you chose. So their sum of the squares is 4 squared plus 3 squared. That's 16 plus 9. That's 25. The difference of their squares is 4 squared minus 3 squared. That's 16 minus 9. That's 7. And twice the product is 2 times 3 times 4, and that's 24. And so these are the three results that we got. And it says those three numbers are the sides of a right triangle. And in fact, we would check that by doing 7 squared plus 24 squared, and we would find out that it does equal 25 squared. Okay, so they're supposed to do that with they're supposed to investigate that by doing 3 different pairs of integers. The adjustment that they would need to make to this is they need to pick any two positive integers, because 0 is not good. And if you pick one negative and one positive, that will not work either, because you'll get this number being a negative, and we can't have a negative side. And so pick any two positive integers, and then you'd be fine. So now they want a precise statement of that, and that's a little challenging, but we're going to give it a try. This is within your student's range. It's just a little tricky. So if you did Jeremy's problem mostly together, then this one you could help them get this statement. If you let x equal the first,